Okay, so there's one more thing that we really need to note about the voltage across the primary winding and the voltage across the secondary winding. Because the high voltage winding A, which is this side here, and the low voltage winding A are magnetically coupled, right? Because they are magnetically coupled, we know that the voltage across the phase A winding will be in phase with the voltage across the secondary winding, which we also define as VAG. Okay, so they're going to be in phase. Why? Because they're the two windings are magnetically coupled. They will be in phase, but that doesn't mean that the magnitude of the high voltage winding is going to equal, so it's not going to equal the magnitude of voltage on the low voltage winding. So the magnitudes will definitely differ, right? The magnitudes will differ, but whatever the magnitudes will be, they will be in phase, okay? So that's one characteristic that we really need to understand. Okay, so before we explain that concept in this phasor diagram, if you haven't already, please click on the bottom right corner of the screen. There should be a subscribe button. Please subscribe to this channel. So here's the open form phasor diagram for the illustration that we did above. Okay, now this illustration comes from the previous video tutorials. So if you haven't watched previous video tutorials, this won't make very much sense. What we're saying is that this phasor here, right? We've defined this phasor as the voltage across line A and B, which is equal to the voltage across winding A on the high voltage side, right? And what we said was the low voltage side will have the same phase as this phasor, but the magnitude will be different. So this right here is an illustration, this orange phasor here is an illustration of the low voltage winding, okay? It's the same phase as V phase A, but the magnitude of it is smaller, right? It's a low voltage winding, so the magnitude is smaller. So I'm going to define this as V phase A, which is equal to VAG on the low voltage winding, okay? Similarly, we're going to represent the low voltage winding B and C in this phasor diagram. Okay, so there you have it. This phasor here represents the voltage across the low voltage winding, and as you can see, it's in phase with the voltage across the high voltage winding for winding B, but the magnitude of it is obviously smaller. The voltage across the low voltage winding for winding C is in phase with the voltage across the high voltage winding for winding C, but the magnitude of the low voltage winding is smaller. So that's how you represent the high voltage winding and the low voltage winding for the Delta Wye Transformer connection. This was a necessary step to understanding the phase shift. In part 7b, we're going to analyze how this transformer connection is defined formally like this, and then informally like this. If you want to know when part 7b is going to come out, please go ahead and subscribe. This video was brought to you by GeneralPAC.com, making power system protection, automation, and controls intuitive.